A cat sealed inside a box. Inside that box, a single radioactive atom, a Geiger counter, a vial of poison, and a mechanism that releases the poison if the atom decays. According to quantum mechanics, until someone opens the box and looks, the atom exists in a superposition of having decayed and not having decayed. And if the cat's fate is tied directly to that atom, then the cat itself, according to a strict reading of the mathematics, should also exist in a superposition, simultaneously alive and dead, until the moment of observation collapses that possibility into one definite outcome. This is probably the most famous thought experiment in the history of physics. It has become a symbol for everything mysterious about quantum mechanics, printed on T-shirts, referenced in television shows, treated as proof that the universe allows genuinely paradoxical states of existence. And almost none of that popular reputation reflects why Erwin Schrödinger actually proposed it. He did not design the thought experiment to demonstrate that superposition was real and delightful. He designed it as a criticism, a pointed objection, intended to expose what he saw as an absurdity at the heart of the standard interpretation of quantum mechanics in 1935. Understanding what Schrödinger actually meant transforms this thought experiment from a piece of quantum trivia into one of the sharpest, most productive questions in the philosophy of physics. Here is the real question this video is going to answer. Was Schrödinger's cat really meant to prove that objects can be alive and dead at once? By the end of this video, you will understand why Schrödinger intended the opposite of what popular culture usually assumes, why the thought experiment exposes a genuine, unresolved problem in quantum mechanics called the measurement problem, and why the cat itself was never really the point. Let's start with why this matters beyond a clever story. The measurement problem that Schrödinger's cat illustrates is not a solved footnote in the history of physics. It remains one of the most actively debated questions in the foundations of quantum mechanics today, directly connected to ongoing research in quantum computing, quantum error correction, and our basic understanding of where the boundary lies, if any boundary exists at all, between the quantum world of atoms and the classical world of everyday experience, including cats. Before we get into what Schrödinger actually meant, we need to understand the piece of quantum mechanics his thought experiment was built to challenge: superposition. In quantum mechanics, a system can exist in a combination of multiple possible states simultaneously, described mathematically by something called a wave function, rather than existing in one single definite state the entire time. A radioactive atom, before being measured, can be described by a wave function that includes both has decayed and has not decayed as simultaneous possibilities, each with a certain probability, until a measurement is performed. When a measurement occurs, the wave function appears to collapse and the system settles into one specific definite outcome, decayed or not decayed, with a probability matching the mathematics. This idea on its own already sounds strange, but by 1935 it had been confirmed through numerous experiments at the atomic scale. The double-slit experiment, the behavior of electrons in atoms, the statistics of radioactive decay, all of these matched the predictions of superposition and probabilistic collapse with remarkable precision. The interpretation that treated this collapse as a real physical event, championed largely by Niels Bohr and often called the Copenhagen interpretation, was rapidly becoming the dominant way physicists understood quantum mechanics. Here is the intuition most people carry into this topic, an intuition that actually needs to be examined rather than simply assumed. Many people assume that superposition is a strange but fundamentally atomic scale phenomenon, something that applies to electrons and photons, but obviously stops applying somewhere before you reach the scale of everyday objects. A tennis ball is never observed to be simultaneously in two different locations. A cat is never observed to be simultaneously alive and dead. This intuition treats the quantum and classical worlds as naturally separate domains, governed by different rules without ever quite explaining where or why one set of rules stops applying and the other begins. This is precisely the gap Schrödinger wanted to expose. He was corresponding with Einstein throughout 1935, and both physicists shared deep reservations about the Copenhagen interpretation, though for related but distinct reasons. Schrödinger's specific concern was this: if quantum mechanics is truly a complete, universal theory, applying to all physical systems without exception, then there should be nothing in the mathematics itself that prevents superposition from scaling up to macroscopic objects. The equations governing quantum mechanics do not contain a built-in size limit, a rule stating superposition applies below this scale and classical definiteness applies above it. No, if a single atom can exist in superposition, and if a macroscopic object's fate can be made to depend directly and mechanically on that atom's state, then strict application of the same mathematics should allow the macroscopic object to inherit that superposition as well. So Schrödinger constructed his famous scenario specifically to force this implication into the open, using deliberately absurd, vivid imagery. A useful way to picture his intention is to imagine him holding up a magnifying glass to the Copenhagen interpretation, not to celebrate it, but to show precisely how strange its literal consequences become once you stop confining superposition to abstract atoms and instead extend it honestly and consistently to something as intuitively definite as a living cat. But the cat itself was only a device. What the physics was actually meant to expose was a conceptual gap. The theory did not specify where or how or why the strange quantum rules should ever stop applying and hand control over to ordinary classical certainty. In his own writing, Schrödinger described the scenario as quite ridiculous, using almost exactly that language to characterize the idea of a cat existing as a blurred mixture of alive and dead states. He was not proposing this as a real, expected physical possibility. He was using it as a reductio ad absurdum, a classic logical technique where you follow an argument's own internal logic to an obviously unacceptable conclusion, specifically to argue that something in the standard picture must be incomplete or missing. Schrödinger's real target was a specific, precise question that remains, remarkably, without full consensus among physicists even today. What exactly counts as a measurement, and what physical process actually causes a quantum superposition to collapse into one definite classical outcome? This is the moment of change in our understanding of the thought experiment, the point where we shift from silly paradox about a cat to serious unresolved question in physics, now widely known as the measurement problem. The mathematics of quantum mechanics describes two very different kinds of processes. The first is called unitary evolution, a smooth, fully deterministic, and completely reversible mathematical process governed by the Schrödinger equation, which describes how a quantum system's wave function changes continuously over time, so long as no measurement occurs. The second is collapse, an abrupt, probabilistic, and seemingly irreversible jump, where the wave function suddenly picks one definite outcome from among all its possibilities the moment a measurement is performed. The deep, still unresolved puzzle at the heart of the measurement problem is this: quantum mechanics uses two fundamentally different types of mathematical rules to describe reality, one continuous and reversible, the other discontinuous and irreversible, and the theory itself does not clearly specify exactly when or why a physical process should be treated as unitary evolution rather than as a measurement-triggering collapse. Now we arrive at the deepening, the part where we need to walk through, carefully and honestly, how physicists have actually tried to resolve this gap over the decades since Schrödinger first posed his challenge, because several genuinely different approaches now exist, each with real, serious physicists defending it, and none has achieved full, universal consensus. The first major approach is called decoherence, developed substantially from the 1970s onward, and it represents significant real progress on part of the puzzle, though not importantly, the entire puzzle. Decoherence theory shows, mathematically and experimentally, that when a quantum system interacts with a large, complex environment, such as the air molecules, photons, and countless particles surrounding a cat inside a real physical box, the delicate quantum interference that makes superposition observable and meaningful rapidly leaks out into that environment, becoming so thoroughly entangled with billions of surrounding particles that any practical possibility of observing genuine quantum interference effects at the macroscopic scale disappears almost instantaneously. In this sense, decoherence explains, with impressive experimental support, why we never actually see macroscopic superpositions in ordinary daily life, even if quantum mechanics doesn't forbid them outright. Because any such superposition becomes so entangled with its surrounding environment so quickly that it becomes, for all practical purposes, indistinguishable from a simple classical probability. However, and this distinction matters enormously, decoherence explains why we don't observe interference effects at large scales. It does not, on its own, explain why we experience one single definite outcome rather than a mixture, nor does it fully explain what physically constitutes the final act of measurement itself. Decoherence solves an important piece of the puzzle. It does not, by itself, solve the entire measurement problem. The second major approach is the many worlds interpretation, first proposed by Hugh Everett in 1957, which takes a radically different strategy. Instead of trying to explain why collapse happens, it denies that collapse happens at all. In this interpretation, the Schrödinger equation, the smooth, deterministic unitary process, is treated as the complete and only description of reality, with no separate collapse process required. When a measurement occurs in this view, the universe itself effectively branches, and every possible outcome actually occurs, each within its own separate, non-communicating branch of an ever-expanding universal wave function. In this interpretation, the cat is never genuinely a paradoxical blur of alive and dead. Instead, upon measurement, reality branches into two distinct, equally real outcomes. One in which observers find a living cat, and one in which different observers find a dead cat, with no version of the cat itself ever experiencing anything as blurred or contradictory. Many worlds resolves the mathematical inconsistency Schrödinger identified by removing collapse from the theory entirely, though it introduces its own famously strange consequence. An enormous, continuously branching multiverse of parallel outcomes, a price many physicists find deeply counterintuitive, even while others find it mathematically elegant and preferable to an unexplained collapse process. A third major approach involves interpretations that add new physics specifically to explain collapse as a genuine objective physical process, rather than treating it as a mysterious side effect of observation. Theories like the Girardi-Rimini-Weber model, sometimes called spontaneous collapse theories, propose that wave functions undergo a tiny, genuinely random, spontaneous collapse process at all times for every particle, but with an extraordinarily low probability for any single particle. For an isolated atom, this spontaneous collapse would be so rare that superposition could persist essentially undisturbed for extremely long periods, matching what experiments with individual atoms actually show. But for a macroscopic object like a cat, made of an astronomically large number of particles, the combined probability that at least one of those particles undergoes spontaneous collapse within any tiny fraction of a second becomes overwhelming, forcing the entire macroscopic system into a definite state almost instantly. This approach directly modifies the mathematics of quantum mechanics itself, introducing new physical parameters that, in principle, could eventually be tested and either confirmed or ruled out through sufficiently precise experiments, an active area of ongoing experimental research today. There is also the pilot wave theory, originally developed by Louis de Broglie and later substantially extended by David Bohm, which takes yet another distinct approach. In this interpretation, particles always have definite real positions at all times, guided by an underlying wave that itself evolves according to the Schrödinger equation. What appears to us as probabilistic collapse is, in this view, simply our own practical ignorance of a particle's precise initial position, not a fundamental indeterminacy built into reality itself. In this interpretation, Schrödinger's cat is never actually in a genuine superposition of alive and dead. It has a single, definite, real status at all times. We simply don't know which one it is until we look. Pilot wave theory restores a form of determinism to quantum mechanics, at the cost of introducing a specific kind of non-locality, connecting distant particles instantaneously, similar to the non-local correlations we explored in our episode on quantum entanglement. It is worth pointing to one specific, concrete example of how far experiments have actually pushed this boundary, because it grounds the abstract debate in real laboratory results rather than pure speculation. In 2010, a team led by Aaron O'Connell created what was, at the time, described as the first mechanical object placed into a genuine quantum superposition state. A tiny resonator, visible without a microscope, cooled to near absolute zero, and manipulated to exist in a superposition of vibrating and not vibrating simultaneously. This experiment did not create a Schrödinger's cat in any literal sense, but it demonstrated that quantum superposition is not confined to individual atoms and photons, extending instead to objects containing trillions of atoms under sufficiently controlled laboratory conditions. Since then, researchers have continued pushing this boundary further, using increasingly larger molecules and increasingly larger mechanical systems, each new result narrowing the gap between the microscopic world Schrödinger was defending and the macroscopic world his cat was meant to provoke us into questioning. It is important to be honest here about evidence, interpretation, and speculation, precisely because this topic invites confident-sounding claims that outrun what physics actually establishes. The experimental evidence for superposition itself, at genuinely microscopic and even surprisingly mesoscopic scales, is extremely strong and well established. Experiments have successfully demonstrated superposition-like behavior in molecules containing thousands of atoms and in tiny mechanical oscillators cooled to near absolute zero, pushing the boundary of where quantum effects remain observable further and further toward genuinely macroscopic scales, though still nowhere close to the scale of an actual cat. What remains genuinely unresolved and actively debated among serious physicists today is the deeper interpretive question: whether collapse is a real, objective physical process requiring new physics to fully explain, whether it can be fully accounted for through decoherence, combined with some deeper reinterpretation of probability itself, or whether, as many worlds suggests, there is no collapse at all, only branching. No experiment conducted so far has definitively settled which of these approaches correctly describes what is actually happening underneath the mathematics. Let's bring this together into the insight this entire episode has been building toward. Schrödinger's cat was never intended as proof that ordinary macroscopic objects can genuinely exist as blurred mixtures of contradictory states. It was constructed as a deliberately sharp, deliberately uncomfortable challenge, designed to expose the fact that quantum mechanics, as originally formulated, contained a genuine, unresolved gap. A theory that used two fundamentally different types of mathematical rules, continuous and deterministic on one hand, discontinuous and probabilistic on the other, without clearly specifying when, why, or through what physical mechanism the transition between them actually occurs. Nearly a century later, this gap, known formally as the measurement problem, remains one of the most genuinely open, actively researched questions in the foundations of physics, studied through decoherence theory, through many worlds cosmology, through objective collapse models, and through pilot wave mechanics, without full consensus on which approach, if any single one, correctly describes the underlying reality. The deeper lesson connects directly to the ideas we've built throughout this series. Just as gravitational time dilation revealed that time is not a fixed universal backdrop, and entanglement revealed that separateness is not as fundamental as intuition insists, and cosmic expansion revealed that space itself is not a passive container. Schrödinger's cat reveals that the boundary between the strange quantum world and our familiar classical experience is not the clean, well-understood dividing line most of us assume it to be. It is, instead, one of the deepest open questions physics has ever posed to itself, hiding inside what looks, on the surface, like a simple story about a box and a cat. This raises a further question that this entire series has been quietly building toward. If information about a quantum system's precise state matters this much to the foundations of physics, what happens to that information under the most extreme conditions the universe can produce when matter falls into a black hole? That question will take us to one of the deepest unresolved tensions between quantum mechanics and gravity itself. This has been Planck's Edge. Thank you for stepping past the edge of what you thought you knew about the cat that was never really the point.